In the last video, we had gotten to this point where we had determined the angular momentum of this point particle about this position when it's in this orientation is just going to be RMV by magnitude. We talked about the vector nature, but let's do it by magnitude here. L is equal to RMV, and we had done that with this explicit calculation of R cross P. Well, we have another way to calculate angular momentum, and it's I omega. Right, so first of all, let's calculate the angular momentum of this particle using this method and see if we get the same answer. If we don't, we did something wrong. First of all, let's talk about the omega. It might be surprising that this particle moving in a straight line has an angular velocity, but I'm going to go to the same reasoning I did for the angular momentum. If you're pointing at this thing as it goes by you, your arm is describing an arc, right? I'm pointing it as it comes, it's right here, and it keeps on going and describing an arc. So it has an angular velocity about this point. Where we are right here, we are this r away. It might be helpful to express that angular velocity in terms of a linear velocity. I know how to do that with the tangential velocity. And at this point, where the velocity and the r vector form a 90-degree angle, this will be the tangential velocity of this particle. So if I remember my handy equation, V tangential is equal to R omega, that means omega is equal to V tangential over R. So I can substitute that in here now. What's left is to determine the moment of inertia of a point particle. And as it turns out, that is mr squared, where r is the distance between my point of summation and the particle itself. In this case, that's just going to be this distance, r. So the moment of inertia is mr squared. My omega is v tangential over r. I'm going to lose an r, and I get mr v. I'll leave off the tangential, because at this point, what we're saying is v is tangential to this position. So yeah, I get the same thing that I got before, which of course I have to do because I'm calculating the same quantity. But that's two different ways, the explicit cross product and the other formula that I have is I omega. So both of them will work. In general, you can use these interchangeably depending on what is easier. Usually, if you have an object rotating about an axis, the whole rigid body rotation, the whole thing is rotating about an axis. This is what you're going to do. If you have a point mass rotating about some other point outside of itself, you typically choose this R cross P. But really, you're free to do either one. There are some ways to do it that are more clever than others and less work, but it's your choice. Both of those equations will work just fine. All right, so a couple of other things to talk about. We had, at some point in the past, formed a Newton's second law in linear form. And then we had pointed out that this is actually a special case of Newton's second law for situations in which the mass doesn't change. Now, that's a large majority of the situations we're going to deal with in this course, and actually in a lot of your courses. And that works just fine, but this is a specific case of a general equation. So the way Newton expressed this was this, the time rate of change, the time derivative of the linear momentum. Okay, well, let's do some more analogous work. We know the rotational analogy of a force is a torque. We know that the rotational analogy of linear momentum is angular momentum. We know that there is no rotational analogy of time because that's not a vector quantity. So it looks like I can write this down. The sum of the torques is equal to dl dt, and that turns out to be true. So here's Newton's second form in its full glory as the time derivative of the momenta. For the forces, it's the linear momenta. For the torques, it's the angular momenta. So that is Newton's second law in its full version.